Thank you very much. Actually, we're not doing this via Skype. I'm in the room next door, and I just ran a cable over to your screen. Oh, well. On this, who is K9? Pardon? Okay, on the who is K9LA screen, up in the upper right, that's my novice station back in '61. It was a national NC60 receiver that I used for shortwave listening prior to getting licensed. And a good old Heathkit DX35. It's a bug. I started with a straight key, but graduated to a bug. It was a lot easier than a straight key. In the bottom right is just a picture of the team that went to YK9A Damascus, Syria back in February 2001. We had a great time. And of course, that was before 9/11. So things went very well there. Okay, what we'll cover is the solar-terrestrial data at www.qrz.com and its relation to propagation. Once we get through that, we'll go through a quick update on cycle 24, what to expect for propagation at solar minimum, and also some words on cycle 25. So here's what I captured one day, the panel at www.qrz.com. There's a lot of nice, colorful stuff there, so let's dig down a little deeper. What I believe is important is what's in the box, the blue box. That's the solar flux index, SFI, and SN, sunspot number. So what they do is give us an idea if the maximum usable frequency, the MUF, the MUF, is high enough for 17 meters through 6 meters. Now, why I started at 17 will be explained a little bit later when I talk about propagation at solar minimum. The other two indices are the A index and the K index. And what they are is just a measure of how the Earth's magnetic field is being perturbed. And they indicate if there are geomagnetic storms that could disrupt the F2 region. That's mainly the region we're interested in. Usually I'm talking to DX types and contest types, and that's where they usually make their most contacts, via the F2 region. Now the A and K index are tied to coronal mass ejections, CMEs, and coronal holes, CHs. So we'll get to that in a little bit too. So SFI and SN. Well, SFI is the 10.7 centimeter solar flux index. Now, a wavelength of 10.7 centimeters is a frequency of 2,800 megahertz. So that's up there quite a way. Because of the relatively long wavelength of 10.7 centimeters, it has nothing to do with ionization. It's just a proxy for the true ionizing radiation, which is extreme ultraviolet, EUV. Now, the range of the solar flux is from about 65 at solar minimum up to 300 or more when we hit a solar maximum. And there are what the solar flux needs to be for days and maybe even a little bit longer to have 15 meters, 10 meters, and 6 meters open. So that'll give you a good idea. We're bouncing around 65 right now, so that means 15, 10, and 6 meters really aren't doing very well. And it also indicates where it's solar minimum. In a similar manner, the sunspot number ranges from 0 at solar minimum. We've had lots of 0 sunspot days recently. We've had them before at other solar minimums, so this is nothing new yet, unless it goes on for a while. And the maximum sunspot number is 200, a little bit more than that, and that's what happens at solar max. And that second bullet under sunspot number tells us if you're using a sunspot number, what we need for 15, 10, and 6. So if we're at 0 sunspots right now, does not bode very well for 15, 10, or 6 meters. Of course, we got to remember that 6 meters also can have sporadic E openings, which generally have nothing to do with the solar cycle. Now, we mentioned that 10.7 centimeter solar flux has nothing to do with ionization. So the bottom left is a picture of the sun's radiation at various wavelengths. You can see where visible light is, and that's the most intense radiation that the sun puts out. And of course, that's why our eyeballs work so well with visible light, because that's how it all works out. There's 10.7 centimeter solar flux in red, and that's about where it is. But what's important is on the left side of the screen, there's a annotation ionizing wavelengths from about 0.1 to 121.5 nanometers. So you can see that 10.7 centimeter solar flux is way far away from the true ionizing wavelengths. And the sun does not put out that much energy at those wavelengths, but fortunately it's good enough to ionize atmospheric constituents. And there's just in yellow text is basically the wavelengths that ionize the 3 regions of the ionosphere. F2 region is extreme ultraviolet, 10 to 100 nanometers. For the E region, it's mostly what's called soft X-rays from 1 to 10 nanometers. And for the D region, hard X-rays, 0.1 to 1 nanometers. And also 121.5 nanometers, which is the Lyman alpha line. It's a spectral line of hydrogen, and it also ionizes the D region. Okay, now in that upper left-hand panel, there are other parameters that are tied to solar flux and sunspot number. And this slide talks about those parameters in the blue box. The X-ray is just the intensity of radiation at 1 to 8 angstroms. Angstroms is an optical measurement. Generally, it's better to talk in terms of nanometers for radio, and that's 1 to 0.8 nanometers. And X-rays really have an impact on the D region. Now, the X-rays are driven by solar flares. Flares are classified as A, B, C, M, and X. A is the smallest flares, or A is the smallest flares. B, C, I don't know why they skipped D through L, but they did. And I don't know why they skipped N through W. So I don't know, whatever. That's what we have, the 5 categories. And the higher the letter generally means increased D region absorption. So on the day I captured that, A 6.0 says it's hardly any flaring at all from the sun. The 6.0 is just the scale for how much of A there is. It's a logarithmic scale, so it's 1 to 10, and then it moves up to the B scale, which goes from 1 to 10, then it moves up to the C scale. So A 6.0 is pretty quiet. The 304A, that's the intensity of radiation at 304 angstroms. That translates to 30.4 nanometers, and the number displayed is divided by 1 e to the 8th, 1 times 10 to the 8th. So to get the true intensity, you have to multiply that 89.4 times 1 times 10 to the 8th. Now, if you remember, 30.4 nanometers is what ionizes the F2 region. So that's a good indication of what's going on with the F2 region. Now, numbers from about 80 to 100 is solar minimum. At a big solar max, we can get up to 400. So again, in addition to solar flux and sunspot number, the 304A parameter would give us an idea where we are in a solar cycle, and also what the F2 region is doing, if it's doing anything, or hey man, 10 meters is open. A and K. Okay, it all starts with the K index. Generally what's given is a planetary K index. In other words, a bunch of observatories around the world take measurements, and then a planetary K index, KP, K sub P, is given. It's a 3-hour parameter, and it measures how active the Earth's magnetic field is in that 3-hour period. Now, the 3-hour periods are 0000 UTC to 0300 UTC, then 300 to 600, etc. So there are 8 K indices throughout the day. The K index is on a logarithmic scale. It goes from 0, which means the Earth's magnetic field is very quiet, to 9, which means the Earth's magnetic field is extremely disturbed. And like I said earlier, when the K index is low, that means the F2 region is doing really good. If the K region is very high, that usually means that the F2 region is depleted of electrons, which means the MUF, the maximum usable frequency, has been lowered. Now, the A index is usually given as a planetary index also. What it is a daily parameter. It's yesterday's parameter. And again, it's the activity of the Earth's magnetic field, and it's the average of yesterday's 8 K indices. It's on a linear scale. Quiet is 0 and extremely disturbed is 400. So just like the K index, you can evaluate what's going on with the Earth's magnetic field by looking at the K and the A index. Now you have to go through some manipulations in math to average the K indices, because they're a logarithmic scale and you can't really average logarithmic scales. So you have to convert the K index to a linear scale, and then you can come up with the A index, but that's another story for another day. In general, we want low A and K indices. That means the Earth's magnetic field is quiet and the F2 region is as good as it's going to get. High A and K generally means the lower F region MUFs, which, for example, if 20 meters was open and the A and the K index spikes up for a long period, then probably 20 meters wouldn't be open. Okay, there's some other parameters tied to the A and K indices on that panel too. And we'll talk about those that are in the blue box. The PTN FLX, that's the proton flux in the solar wind. And if that number's much, much greater than 50, that means a big flare happened. And one of our cats just showed up. Hopefully he won't step on the keyboard here. Yeah. Oh boy. Hold on here. Let me kind of guide him out of the way a little bit. If that proton flux is elevated, 50 more or more, that means there's an increased absorption in the polar cap. So the polar cap is that area within the auroral zone. So if you're trying to work over the pole, like into India or deep Russia, you might be affected, and it might be a bad path. The ELC FLX is the electron flux at geosynchronous altitude. In other words, measured by a satellite up at 22,000 miles or whatever that geosynchronous altitude is. A large number like 127 says there are a lot of electrons are still trapped up in the Van Allen belts. So they're not coming out and causing aurora. So ideally, we'd like the electron flux to be high. Okay, the AUR, or the aurora, says how much energy in an auroral event, and higher is bad. Now, on that day, they didn't report any, so the auroral activity was pretty quiet. The aurora lat, AUR lat, is the lowest latitude for possible aurora. Now, the higher the K indice, the lower the latitude. Now, recently, we just went through the 160th anniversary of the Carrington event, which was a massive coronal mass ejection. And aurora was seen in Central America, so that gives you an idea how big that thing was. If something like that hits us today, we'd probably have all kinds of problems with all the electronics we have. The BZ, that's the magnitude of the Z component of the interplanetary magnetic field in nanoteslas. Positive and a small negative value is good. A large negative value is bad. Large negative value means there's probably a coronal mass ejection, and it is coupled into the Earth's magnetic field, and that's going to cause the F2 region to decrease in electron density. SW is the solar wind speed. On average, the quiet solar wind speed is about 400 kilometers per second. It'll get much greater if there's a coronal mass ejection coming or a coronal hole. The highest I think we've ever seen is something like almost 2,500 kilometers per second, which means those the solar wind was moving along quite a lot, and it really messed up the Earth's magnetic field. Okay, the other area to concentrate on is the HF conditions and that solar image. The HF conditions are an assessment of the HF bands. Depending on when you look at it, it'll be fair, good, poor. And in general, the lower bands need darkness. That's because ionospheric absorption is critical. And during the day, there's going to be lots of absorption, so the lower bands won't be very good. On the other hand, the higher bands need ionization. In other words, they need a high MUF. And that means, like I said, the ionization is critical. So if the solar flux index and the sunspot number and that 304 angstrom number are high, probably you'll see good for the higher bands instead of poor. Geomag field is just words describing activity. Very quiet, disturbed, extreme, etc. And again, as it's more disturbed, that hurts the ionosphere. Sig noise LVL is an S meter rating of how noisy the bands are. And of course, low is best. The MUF US Boulder, that's the maximum usable frequency in megahertz at the Boulder ionosonde. And that assumes that Boulder is the midpoint of a 3,000 kilometer path. So if you see the 10.2 megahertz, that means 30 meters should propagate over 3,000 kilometers with Boulder at the midpoint of the path. And of course, that'll depend on the time of day, the solar flux index, and the sunspot number. The solar flare probability is just the probability of a flare. Remember, for this panel, we were at A 6.0, which means the probability should be very low, and indeed it is, 1%. And there's a current solar image looking at the sun at 30.4 nanometers. In other words, it's looking for regions that would help the F2 region. And of course, at Solar Min, we don't see many of those. That's why it's kind of all red. It's all blank. The final part of the panel is the VHF conditions. And it's just a general assessment of VHF bands in terms of aurora, sporadic E, and moon bounce and moon bounce. You can see the aurora status. It says the band is closed. That means there's more auroral activity, which might help a VHF, auroral contacts, point your antenna north and work somebody off of scatter, reflection, refraction from the auroral zone. And there's the next four are what's going on with sporadic E on 6 meters, 4 meters, which is Europe, 2 meters in Europe, and also 2 meters in North America. It looks like on that day there was some high MUFs, high enough MUFs for 2 meter sporadic E contacts in Europe. Okay. Now the EME degradation, that's kind of an assessment of what's going on, what could be happening with moon bounce, and it said there's a fair degradation in moon bounce. So if you're on moon bounce, it may not be too good. Probably doesn't apply to many of us. Now, at the bottom, there's some colors. The MUF is color-coded. The gray means there's no ES activity, no sporadic E activity. If there's blue, that means 6 meters has been reported to have some sporadic E contacts. If it's green, there's sporadic E reported on 4 meters. If it's yellow, conditions could support 2 meter sporadic E. And red means there is sporadic E on 2 meters. Now you'll notice that the MUF extends over the time period from 0 to 2400 UTC. So you can see the blue, which was 6 meter ES reported, was around 6, 7, 8, about 0900 UTC. And of course, you'd have to convert that to local time. The MS, the meteor scatter activity, you got to use that scale at the bottom. There's lots of yellows and orange and red, and you can see at the bottom there it goes from blue to red. So during the time frame 0 to about 1100 UTC, the meteor scatter activity was best around 6, 7, 8, 900, 0900 UTC. So this is mostly for VHF type operators, and there are lots of other websites to give an indication what happens. There's a website that tells if it's possible for tropospheric propagation to occur, which could mean 2 meters and above, propagates for extreme distances, at least more than line of sight. Okay, some comments. The goal of the solar-terrestrial data is to provide data to assess propagation, right? But we got to watch it, because we try to take all that data and reduce very complicated processes into simple generalities. That can be tough to do. And what happens is you lose some short-term ionospheric events that just aren't captured. Now, some can have a positive effect. So just be aware, when we try and simplify all that data, we could be losing some interesting happenings. Now, all that data at qrz.com is explained on that website, at 0NBH's website. So you can go there and refresh your memory and all that, or to look at the slides here. He's got a lot of stuff, so it's pretty interesting. You can probably spend days there. Okay, hopefully we're done with trying to understand what all those things mean. There won't be a quiz later, so don't worry about it. Here's the cycle 24 in terms of 10.7 centimeter solar flux. You can see that it doesn't look like we've reached the bottom yet, but for all intents and purposes, the higher bands are at solar minimum. Okay, two questions. Why were there two peaks in cycle 24? Notice the red line to the right. That's the prediction for what the solar flux is going to do as we move into 2020 and beyond. And is the prediction, which is 59.8, if you expand the scale, that's what it is that a reasonable prediction? And how long are we going to be at solar minimum? That's probably the most interesting question. Well, why were there two peaks? That's because the two hemispheres of the sun aren't in phase. The northern hemisphere generates more sunspots, and then it quiets down, and then along comes the southern hemisphere, and it generates a whole bunch of sunspots. Now, if they did that at the same time, that would give us a very big peak, kind of like cycle 19, which is shown to the left. And you can see cycle 19, mostly the northern hemisphere was the really active region. Now you can see we've seen double peaks on cycle 22, cycle 23, and cycle 24. But the sun appears to be in new territory because we haven't seen anything like this prior to cycle 22. Our records go back to about 1750, and we don't see double peaks. Now you got to watch it. How good was the data back then? And that's always something just to consider. So maybe maybe the data just isn't good back there, and this is really nothing new. Now, it's very well possible that many double peaks occurred well before we started recording sunspots. But unfortunately, we don't have any of that data. So that prediction of 58.9 for the solar flux really raised some eyebrows, because most of us, I think, have grown up thinking that the lowest solar flux we'll ever see is about 65. So I got kind of interested. I downloaded the solar flux index from the Canadian people who take the data. And darned if back in 1955, there was a solar flux reading of 61.6. That's pretty low. And what the 58.9 suggests is we're in for a deep solar minimum. Now, that's not good news for those who like the higher bands, but that's maybe what's happening. Now, notice that the daily 10.7 centimeter solar flux has adjusted in parentheses in the title. Now, you got to remember that Earth's orbit around the sun is not a perfect circle. It's closer to the sun sometimes and farther away. So the solar flux is translated to an average distance between the Earth and the sun of 93 million miles. That's what adjusted means. There's other data that's observed, and it's just the raw data taken at 10.7 meter solar flux, but it's good to translate it to a consistent distance. So how long are we going to have a solar minimum here? Well, here's a picture of solar minimums between cycles 18 through 19, all the way up through 22 and 23. Now, the plot shows how many months the smooth sunspot number was below 20. Okay. And you can see that 1, 2, 3, those 5 solar minimums, well, they only lasted about 2 years from when the smooth sunspot number went below 20 to when it ascended through 20 again. So we got used to that. About 2 years, and that was good. So we just had to wait 2 years for solar minimum, and then the next cycle would be starting up, and we'd be working 10 meters rather quickly. But the minimum between cycle 23 and 24, that was the last solar minimum, it went out almost 5 years. So something's happening. The sun's magnetic field is weakening, and it just drug out solar min more and more. Here's the current solar minimum in red. It looks like we're tracking another long solar minimum. Now, will it hit bottom around 36 months after it descended through a smooth sunspot number of 20? That puts it around right now, September 2019 or so. But it's hard to say what's going to happen. That red line may go down there and stay down there for a while, or it may follow the green, which that'd be nice to finally get out of the solar minimum. So what happens at solar minimum with respect to propagation? Well, the low band should be very good. And of course, you should always pay special attention to sunrise and sunset times. The low bands need the dark ionosphere. So if you have a mapping program like what's in W6EL prop, you can see how your path is with respect to daylight and nighttime, and also sunrise and sunsets at both ends of the path. Now, even though there's 0 sunspots for quite a while, there's still enough extreme ultraviolet to allow 20 meters and 17 meters to a lesser degree to offer worldwide DXQ cells. So there's always 20 meters throughout a solar cycle. 15, 12, and 10 right now may have some occasional openings of a north-south nature, like into South America, and maybe even to Australia and New Zealand, VKZL. That's because the paths to VK and ZL stay at low latitudes, and the equatorial ionosphere is really the most robust region of the ionosphere. So it can help the higher bands, even at solar minimum. Like I mentioned before, don't forget 10 meters and 6 meters sporadic E in the summer and in December. It looks like we've pretty much gone through the summer season, so we should get ready for December and hope we have some stuff that we can dust off the 6 meter band switch. So what does a long solar minimum tell us? Well, here's a plot of how long a solar minimum was versus how big the next solar cycle was. And what you can see, although the correlation isn't perfect, the longer you spend at solar minimum suggests that the smaller the next cycle is going to be. It's it's only 23 data samples, so it's not a lot of data, but it gives a general idea that more than likely, if we go 5-6 years, we're going to have another small cycle 25. Now, all that bad news, we have seen the first sunspot of cycle 25. Solar cycles overlap. In other words, we'll see cycle 24 sunspots at the same time we're seeing cycle 25. The first sunspot of cycle 25 was December 20th, 2016. It's circled in red. But it was a very short duration, and it was not assigned an active region, an AR number. which probably means probably won't count as the first official sunspot of cycle 25. How do we tell if a sunspot's from the old cycle or the new cycle? Well, one is where it emerges on the solar disk. New sunspots emerge at the higher solar latitudes, and as the solar cycle progresses, the sunspots emerge closer and closer to the solar equator. Also, the polarity. A sunspot is a magnetic field going out of the sun and coming back in, and we can tell which way that orientation is. So there are two ways to confirm that was a new sunspot from cycle 25, and it's just too bad it didn't last longer. Now, we've seen some more cycle 25 spots in April, November, May of this year, and July of this year. But these were also of a short duration. There were no active region numbers assigned. Finally, though, a long duration cycle 25 sunspot was seen on July 8th, and it's circled in red. It was assigned active region 2744, which probably means it's going to be the first official cycle 25 sunspot. All those prior cycle 25 sunspots are common in a solar cycle. I guess the sun is trying to make up its mind, hey, I'm just going to do something real short and get me ready for more bigger ones. Now, cycle 25 predictions. Well, I've seen about 10 predictions in the scientific literature for cycle 25. The lowest is for a cycle 25 about 2/3 the size of cycle 24, which is not very big. It'll be the lowest in our lifetimes, that's for sure. The highest was 154, which, that'd be nice, but the general consensus among solar scientists is that cycle 25 is going to be another small one, similar to 24, maybe a little bit bigger, maybe a little bit smaller. But remember, although cycle 25 may be small, we may still have worldwide F2 region openings on 10 and 6 around the peak in the fall and winter months. So we'll just have to wait and see. We could be at a minimum 4 years away from a solar cycle peak. It depends how long this solar minimum goes. So, summary. The high band ops, we want a high solar flux index and a high sunspot number, and we want it for more ionization, which means the MUFs are higher. On the other hand, low band operators want low solar flux index and sunspot number, because that means lower ionization, which means there's lower absorption. And as you move down in frequency to the low bands, they cannot withstand absorption like the higher bands. Now, I think we all desire low A and K indices, unless you're a VHF op. You're hoping for high K indices for aurora contacts. Looks like we're in for a long solar minimum. Hopefully the bottom's going to be in late 2019, later this year, or early 2020. But it could extend longer. We'll have to wait and see. The digital modes, FT8 and FT4 now, they're going to make this solar minimum the most active in history on 15, 12, 10, and 6 meters. So if there's no openings on sideband and CW, get on the digital modes. There's usually activity, at least on 15 and 12, and maybe 10 and 6. Their ability to decode signals lower than CW and certainly lower than sideband is a real big help at solar minimum. Expect a small solar cycle. Expect a small cycle 25. And here's one thing that I believe, and it can be confirmed when there's a big contest. The bands are open more than we think. We just don't get on enough to transmit and try and work somebody. And that's what happens when lots of operators get on in a contest. Well, they're going to check the band by CQing and all kinds of stuff, and a lot of times find that, hey, man, that band's open more than we think. A good example was a couple of weeks ago. I had a sked with NR1DX down in Florida, and we started on 20 meters, and it was during the day, and we said, hey, let's go try 17. Well, 17 worked great. Then we said, hey, let's go try 15. So we got on 15 meters, and yeah, no problem at all. So then we said, well, heck, we got to try 12 meters now, and we went there, no problem. Then we got wondering about 10 meters. So we went up to 10 meters, and hey, yeah, the band was open, at least between Indiana and Florida. We tried 6 meters, but that didn't work out too good. So, like I said, the bands, I think, are open more than we think. We just got to get on the air and transmit. So that's all I had. Yep, it sure is. So if there are any questions, I'd gladly, and try and answer them. Okay.
Carl, this is Ron, K5XK. Nice to see you back in the state of Arkansas again. You were with us last December at the ADXA meeting, so welcome back.
You're welcome. It was W3LPL was there in December 2018. I think we were there in 2017.
Well, anyway, in Bella Vista,
Anyway, whatever. Yeah.
It's known as Bella Vista Moment, so sorry about that.
That's okay.
You have been on a number of de-expeditions, and while some of the guys are formulating some questions for you, think about some of those de-expeditions that you were on and outline some of the unusual propagation that even surprised yourself as being much more knowledgeable than most of us. What are some things that you experienced that we might enjoy hearing about?
Okay, well, there's two great examples. When we went to Syria in February 2001, we picked February because we had some big low-band operators with us, and they wanted to make sure that there was lots of darkness between Syria and the U.S. But of course, 2001 was around the peak of cycle 23, so we had some good 10-meter openings. And I remember being on 10-meter sideband one day, later in the afternoon, working the U.S., and what was happening was that there'd be lots of U.S. stations for several minutes, and I'd try and work as many as I could. Then they'd disappear for several minutes. And then later they'd come back, lots of stations, so you work as many as you can. So the band the 10 meters was up and down, and what that means is there are generally events in the lower atmosphere that couple up to the ionosphere, and they cause traveling ionospheric disturbances. And they're of a cyclic nature. So that's what I think was happening. It would have been nice if 10 meters was continually open, because I could have worked a heck of a lot more people, but it really opened my eyes when I saw that cyclic nature in the opening. And it was, maybe 5 minutes between nothing and the next boom. And then the 5 minutes, the next nothing, and so it was pretty good. Now, when we went to OJ0, the Market Reef, that was in July of 2002. Now, think about July in Scandinavia. Well, the sun doesn't go down. So I was trying to make a scad with a W0 on 40 meters because he needed OJ0 on 40. But there was still just too much absorption, even on 40 meters. And so that's a good thing that up at those high latitudes in the summer, man, the low bands aren't very good. What was interesting, we were up that night. I got up and Vicky got up, and I think she was on a band. I don't remember which band she was on, but there was a guy kayaking from Sweden to Finland, and he stopped by Market Reef because he heard the generators on. He knew someone was around. So he come up and said hello, and it was a nice clear night. There was enough light, no problem. The sea was extremely smooth, but it still struck me as kind of funny. Here's a guy in the middle of the night kayaking from Sweden to Finland, but they probably do that a lot in the summer because they got so much daylight hours. So those are the two things I remember the most on the Syria and the Market Reef expedition.
Carl, before we go to any other questions, could we see your face?
Sure. Okay, I'm gonna do that. Actually, I'll put a picture of Tom Selleck up, and hopefully I fool you. Let's see here. How do I get to? Where's? Oh, there's Skype. Yeah. Okay. Hold on here. Turn the camera on. My light up. There we go. That's me.
Do we have any questions?
All right, guys. Talk to us about long path propagation, when to expect it, especially on the lower bands now, and what are some interesting phenomenons you've noticed about long path over the years?
Okay. Well, the two things that determine whether short path or long path is open is how much absorption there is and what's the MUF. So it very well could be that long path offers lower absorption and a high enough MUF, whereas the short path doesn't, because the short path may be in daylight, and that's not good for low bands. In general, long path on the low bands doesn't follow a great circle path. That's because there's just too much daylight. If you look at a great circle path like between Arkansas and Southeast Asia. So I think what's happening is the signal is taking a shortcut across the dark ionosphere. And that's just hypothetical. We have no proof of that. There's other explanations, but I'm not sure we'll ever figure it out. It'd be nice if the scientists, ionospheric scientists, uncovered something in all their measurements, but they're not that very interested in long path propagation on the low bands. One of the best long paths, at least up here in the Midwest, is to Japan in the morning hours when we're near a good solar maximum. And I can remember talking to JH3 Delta Papa Bravo one April morning for about 2.5 hours via long path, which I never figured long path to Japan on 10 meters would last that long, but it did. The band's probably best for the most consistent long path is probably 30, 20, and 17 meters. During the centennial in 2014, we ran W1AW/9, and one of the mornings I got on 17 meters, pointed the antenna to the southeast and worked JAs via long path. And short path was in the dark ionosphere, which meant the MUF wasn't high enough for 17 meters. But going long path to the southeast, around and just after our sunrise, of course, there's a lot of ionization in the daylight, so that's what enabled that path. In general, on the low bands, at sunrise, you should look to the southwest for openings to Southeast Asia. In evenings, you should generally look to the southeast for long path openings to Southeast Asia. And taking the W6 propagation software and using the mapping feature, you can see why that probably happens. It'll show you where the terminator is, where the long path is in relation to the terminator, and why southwest is good at sunrise and why southeast is good at sunset.
I think we have another question.
Sure.
Carl, I've noticed sitting in the shack, I have a vertical antenna as well as some horizontal antennas for the same bands. And working guys either overseas or even here in the States, from time to time on the horizontally polarized antenna, they'll go away and can flip quickly to the vertical and pick them right back up. What's the phenomenon there?
Okay, you got to remember that the ionosphere is immersed in a magnetic field, okay? What that means, it's birefringent. In other words, there are two characteristic waves that propagate through the ionosphere, the ordinary wave and the extraordinary wave. And they're orthogonal. So it could be, well, not could be, it more than likely says one of the characteristic waves is not propagating, but the other one is. Now, in general, at like on 10 meters, both take the same path through the ionosphere, so they could, constructively or vectorially add, or they could vectorially cancel each other. But as you move down in frequency, they take different paths, and that's probably where one could be propagating and the other one isn't, or it could flip and the other one is and that isn't. So that would show up as a change in vertical versus horizontal polarization.
Or as my uncle used to say, it just tumbles.
Well, you got to remember that there are two characteristic waves that propagate through the ionosphere because the ionosphere is immersed in a magnetic field. So, I think what you said is kind of from the days where maybe it wasn't clearly understood that how the Earth's magnetic field affected the ionosphere. The thought was there's just one wave that goes to the ionosphere, but there are really two of them. When you get down to 160 meters, the extraordinary wave is heavily attenuated where the ordinary wave isn't. So that's the one that you predominantly use on 160 meters. Now, of course, the ionosphere is very dynamic and things change and, short-term things happen. So trying to figure out all that stuff can be very difficult.
Thank you.
You're welcome.
Okay. Hi, Carl. I'm James, KA5DBS, and I first want to say thank you for a really informative presentation. It was very educational and appreciated.
Okay.
Just a point, and maybe something will turn into a question, but I don't know if you had seen, there was a paper published in Nature about 2 or 3 months ago talking about long-term solar oscillations and they're looking at sort of baseline oscillations in the solar irradiance and so forth. And the conclusion of that paper is that we're headed into essentially another Maunder type minimum, which is something you alluded to as well. They believe it's going to start in 2020, so basically next year, and we're going to be in that for about 35 years according to their data. So that's the bad news. The good news is there was a sort of puzzling or sort of interesting result in that paper is that they noted as well over their data from the last couple hundred years that we've seen an increase in solar irradiance, not a decrease that we typically would have expected. So the solar irradiance has actually been increasing, has increased by about 3% over the last 200 years. What I'm wondering is, have you seen any data or any information that shows that some of the other factors that you discussed that affect propagation are changing on a longer term scale? Obviously, we haven't had data 10 centimeters for the last 200 years, but I'm just wondering if anybody's looked back over even a short period of time and extrapolated and see if anything's going on there.
Yeah, that's a really good question. Yes, I did see those papers, and the one that sticks in my mind is by Shepard, Zarkov, and Zarkova. And what they did is moved the model of the sun one step forward, hopefully, and instead of using a one-cell dynamo in both hemispheres, they went to 2 cells in both hemispheres. And the result was better, they hope is a better prediction, and that's where that came from. They had a follow-on paper that talked about something like a Maunder minimum. But in their first paper that I saw, they said that there's still going to be solar cycles, they'll just be small. But whether we have nothing or maybe some small ones is, I think, still up in the air. Just remember, even if we have a Maunder type minimum, there's still enough extreme ultraviolet to keep the F2 region there to support 20 meters. So, it's not like everything's going to disappear.